Last class, we studied some of the essential concepts that we need from semiconductor device physics in order to develop the theory of the transistor, right? So we did three things. One is law of mass action, right, which basically says that product of electron and hole concentration is always a constant, and since at intrinsic, for an intrinsic semiconductor, Ni equal to Pi, right, number of electrons, free electrons is equal to number of free holes, it is just equal to Ni squared. Second thing that we studied was the Maxwell-Boltzmann law, which basically says that if you have 2 points in a semiconductor which has a electron concentration, free electron concentration of N1 at one point, 0.1, and at 0.2 it has a concentration of N2, then there has to be a potential difference between these 2 points called psi 12, right, and the relation is given by N1 by N2 is equal to e power q psi 12 by kT. Okay, this was the second thing. And was there any other law that we needed from there? I believe not, right, just with these two. And when I put a PN junction together, right, W, the depletion width in the N region into the donor concentration is equal to the depletion width in the P region into acceptor concentration. Okay, what does this imply? If ND is much greater than NA, it implies that WP will be much greater than WN. The depletion region will sort of go deep into the other side, right, which makes sense because you have a high concentration of charges on one side. In a small distance you can get a lot of charge, whereas on the other side, to get the same charge number of charges, you need to go in a much larger distance inside that because the concentration is much lesser. Okay, these are the three key concepts that we needed, and this is all we will use in developing the entire theory of the MOS transistor. Okay, so now let's get started with a two-terminal device called a MOS capacitor. Okay, MOS capacitor is, what is MOS? It's metal, oxide and semiconductor. That's what MOS stands for. So the way the structure of the device is the following. You have a metal which is called the gate. Then you have a thick oxide. Okay, by thick I mean maybe a nanometer at most, I mean at least. Okay, maybe 3 to 4 nanometers at most. Okay, this is metal, oxide, and then you have the semiconductor which goes pretty deep into this. This terminal, the second terminal, is called the body. So what is this oxide? It is basically silicon dioxide that has a relative permittivity epsilon r of 3.9. Okay, so silicon dioxide is, the advantage is, like I told you last time, is that you just take a silicon substrate, okay, and you oxidize it and you get silicon dioxide. So the interface is going to be very clean, right, between the oxide and the semiconductor. If you don't have a clean interface, as you will see later, that will lead to alterations in the threshold voltage. Okay, therefore you have to ensure that that interface is as clean as possible, right. Now this and this is semiconductor, MOS. Okay, the semiconductor can either be p-type or n-type, right? If I dope it with boron, I get a p-type semiconductor. If I dope it with phosphorus, I get an n-type semiconductor, right? So let's consider the case of a p-type semiconductor, which means I have an acceptor concentration of Na. Okay, Na is boron concentration. What is the typical number? Again, it's about maybe 10 power 15 per centimeter cubed. This is like not very heavily doped. You can go up to 10 power 17, 10 power 18, and that becomes a very heavily doped semiconductor, which we will come to a little later. Okay, so now I can start applying a potential across this gate and body, and we'll see what happens, right? So what I do is I basically apply a plus minus VGB. Okay, so first of all, in this semiconductor, which is in excess, holes or electrons? Holes. So basically holes are majority. Okay, and if the holes are in majority, what is the number of holes available free at room temperature? Na. And therefore what's the number of electrons in this? Ni squared by Na, law of mass action. Okay, so now what do? I apply first I'll apply a negative voltage on this VGB. I'm going to consider three cases. VGB is less than 0. Okay, so 1. So what will happen here? So you have negative charges on this metal here, right? You'll have negative charges sitting here because it's negative, gate is negative with respect to the body, and that has to attract holes to the, it needs positive charges across the oxide for the electric field to terminate, right? Therefore you are going to, now you have lot of holes sitting in the semiconductor, right? Free holes, and therefore those holes will get attracted to this point, right? So effectively there is a charge available for termination, and really there's nothing that is very special about this, because what we have done is we have taken a p-type semiconductor and we have made it even more p-type. If you look at this surface, the surface concentration of holes will be greater than the concentration of holes in the deep in the bulk or the body. Okay, this silicon substrate is also called a body or a bulk. Okay, bulk terminal. So therefore this is not very useful, and this region of operation is called accumulation. You are just accumulating more holes there and you can't do much with that. Okay, so therefore what you do is you start applying a positive voltage. So now what happens? You start attracting positive charges on that metal gate, because VGB is greater than 0, which means now that I need to attract negative charges. Okay, this is my metal, I have my oxide, and then I have my semiconductor. This is gate, body. Okay, so this is, so now I am going to attract get some positive charges on this metal gate here, and now I want to get some negative charges on the other side of the oxide so that I can terminate this electric field because of the positive charges there. Okay. So what will it do? No. So why can't electrons get attracted? Okay, but so let's do a thought experiment. Suppose I attract electrons, free electrons here. Forget about holes getting repelled, let's say. Okay. Then you agree that as I keep increasing my VGB, this will start becoming more and more and more and more, right? Which means at the surface, I am going to have an electron concentration which is different from that of my bulk. So here, electron concentration will be greater than Ni squared by Na if VGB is greater than 0. VGB greater than 0. Okay. Now we know that by the Maxwell-Boltzmann law, the ratio of those concentrations has to have some potential, is equal to e power q some potential by kT, which means that there has to be a potential difference that develops across this point and somewhere in the bulk, right? So it's not possible to directly attract the electrons to the surface. Okay, as you attract electrons to that surface, you need to start developing a potential difference with respect to the bulk, right? And therefore, as he said, the other way to look at it is it's easier to repel the holes initially, right? So what do you mean by repelling the holes? It means that I am going to create the immobile negative charges in the p substrate. So what happens is if the boron gives away a hole, then the boron atom becomes negative and it becomes an immobile charge. So therefore I start creating negative immobile charges first. Okay, doesn't mean there are no free electrons. Free electrons, so as it depletes, now there is going to be a potential difference between the surface and the bulk, some potential difference, and therefore the concentration of free electrons has to go up by some small amount, but that's negligible compared to the number of immobile charge carriers that are available initially. As I continue to do this, you will see that this will keep going on and on and on. Okay, and this will go on until a time when the width or the depth of this depletion region becomes some WD. Okay, and simultaneously I have also attracted some free electrons on this at this point. So the electric field, it does not terminate only at the free electrons, it actually terminates across all of them. You see this? This is how it happens. Something will terminate at the free electron also. It's a combination of both free electrons and immobile negative charges which are in the form of dopant atoms. Okay. So it turns out that as I start attracting electrons to the surface, beyond a point, this surface potential will get pinned. Okay, so I've shown on the left hand side a distance, I will show on the right hand side in magenta here the potential. So this is the surface potential psi s that develops between the surface and the deep in the body. Okay, and of course there is a oxide potential also which is here, psi ox. Okay, on the left hand side I am showing distance, on the right hand side I am showing potential. This is T ox. Okay, and I am going to call this distance here as the length. Into the plane of the paper is the width. Okay, so if I draw this like this, then this width is what I will call W. Okay. So now what you do is you have attracted free electrons, you have created some surface potential. So the question is, will the surface potential keep increasing? Well, it turns out that because it's an exponential relation, right? If you look at the surface charge concentration related to the concentration of electrons deep in the bulk, right, NB, it has to be e power q psi s by kT. So beyond a certain point, a small increase, right, in the surface concentration is like a ln, the surface potential has to go only a ln of that, and therefore it will stop increasing. So if I want to derive the surface potential psi s, it will be kT by q ln of ns by nb. Okay. So if this is very large, if there is enough number of surface charges already available, any further delta change, right, any further change in the surface charges can happen with very little change in the surface potential. So therefore, at some point we say the surface potential gets pinned. It does not get altered after that. The reasonable approximation. When does that happen? So it turns out that this happens when the surface electron concentration is as much as the whole concentration in the bulk. So when it gets pinned, when Ns is equal to Na. So what does this mean? It basically means that I have made my surface as N-type as the bulk is P-type. So I have really reversed or inverted this surface region, and therefore this region, the third region, when VGB is greater than some threshold potential, right, it enters the region of inversion. When VGB is just greater than 0, it is in the region of depletion. It is just depleting the bulk so that it can develop that surface potential in order to invert the channel. So this region is called depletion. So now let us calculate this surface potential that is going to get pinned, right? What is this psi s? Is kT by q ln of, we said that the surface charge concentration should be Na. And what is the bulk electron concentration? Ni squared by Na. It's the whole concentration, that is Na. So this is Ni squared by Na, and therefore you can write this as 2 kT by q ln of Na by Ni, bringing the square out of the ln. So this is a very important surface potential term, 2 kT by q ln of Na by Ni. Okay. So now let us try to first develop an expression for this threshold voltage. What is the threshold voltage? So VTH is the threshold voltage. And what is the definition? It's the gate potential necessary to, gate potential needed to invert Okay, I'll put this in quotes. Invert, it has a very specific meaning, what we discussed earlier. Invert the surface. Okay. So now what we are going to do is, we'll write out this expression, right, and just write the KVL around that loop. VGB is basically psi ox plus psi s, potential across the oxide plus surface potential, plus psi ox. Now what is the oxide potential? It is just charge by the capacitance, right? So because the charge in the at the surface is negative, I am going to write it as minus QD, right? QD prime I will call it by Cox prime. I'll tell you why I am calling this prime. It's a net charge, okay? Of course, this is not true because I also have some inversion charge, right? QD refers to the depletion charge. I also have some inversion charge. So it's only fair to write that this is QI prime by Cox prime. Now what is the capacitance of the oxide? What's the capacitance of the oxide? Epsilon, yeah, epsilon R, epsilon naught, A by D. A is W into L by Tox. Okay, so I am also going to write the equivalent term, which is normalizing it to the area. Cox is going to be defined as epsilon R, epsilon naught by Tox. Similarly, QD and QI prime are basically charge, okay, but QD and QI are charge per unit area. Okay, so now how do I evaluate QD prime? What is QD prime? QD prime is basically the total depletion charge that is available. QI is the total inversion charge that is available. What is QD prime? It is so it's basically every dopant atom that has got ionized is basically the contributing to one QD. Therefore, it's just the concentration into that total volume of the depletion region, right? And what is that volume? It's basically the charge, okay, into the concentration, which is Na, into the volume. What is the volume? WL into WD. So unfortunately, I will not have time to go through all how to get this WD. So we will just take that for granted here. Okay, I hope, yeah, we will just take this expression for granted. WD is root of 2 epsilon SI into, just write that down. WD is root of 2 epsilon SI into mod psi s. I'll tell you why we writing mod psi s, by Q into Na. Okay, this is going to be you can derive this by solving Poisson's equation. Del squared phi equal to the charge density minus Q into Na, and then you solve the differential equation by putting the boundary conditions. You will get this expression, but that you can do in a device physics course. Okay, so the whole point is that WD goes as root of psi s and is inversely proportional to Na. Okay, so now What is QD therefore? QD prime is QNA into W into L into root of 2 epsilon Si mod psi s by QNA, which implies QD prime is that QNA will go and you will basically get 2 epsilon Si into mod psi s into Q into Na, whole thing into the area W into L. So which implies the charge per unit area is just root of 2 epsilon Si to mod psi s into Q into Na. Right? So now what do? I can write my VGB as psi s minus QD by Cox, right, and minus Qi by Cox. I am just splitting this term here. Where is that? Yeah, I am splitting this term, right? Of course, let me be clear. QD prime, because these are all absolute charges. Okay. So what is my inversion charge that is available? It is basically Cox prime into VGB minus the threshold voltage. So therefore VTH is defined as psi s minus 1 by Cox prime into root of 2 epsilon Si mod psi s into QNA. Note that this is epsilon R of silicon, not silicon dioxide, because this is in the substrate, it is in the silicon substrate. Therefore, you are solving Poisson's equation there. The epsilon will come from silicon, not silicon dioxide, right, into epsilon naught. So effectively what is happening, of course there is a minus sign here because it is a negative this thing. Effectively what is happening is, in order to create some inversion charge, right, which is going to be useful for current flow, right, in the form of free electrons, I need to first invert the channel, right, or invert the surface. In order to do that, I first need to deplete part of my body or part of the substrate, and that voltage or that work that the gate voltage has to do in order to invert the channel is basically called the threshold voltage. So even if you apply a large potential, it is only VGS minus the threshold voltage that is actually going to be available for you in order to create more inversion charge and thereby increase the current from there on. Right? Below the threshold voltage, it's like saying that the inversion charge is sort of negligible and you can't do any useful thing with that. Okay.